Good afternoon. My name is Hans-Erik Blomgren. I'm with Katerra on the engineering side. And the segue, though, with Dr. Ling and what you shared, that was brought back some good memories from last summer. We did a lot in a little amount of time. And thanks for steering the ship and teaching, me this experience of being on a shake table. My only regret is the rest of my career is going to be kind of a downer after what we did last summer.
You're going to do a test story.
It was so formative. Oh, you're right. Thank you. Thank you. Sorry. After 2020, it'll go down.
Yeah.
So on the topic, though, in this new role at Katerra, I've been there about 16 months, and I've brought my former colleagues with Arup, and then my first project I got to manage coming to Katerra was this vibration and acoustic performance of residential floor assemblies, and just kind of being on the consulting side for a long time, it was this perceived need that mass timber, one of the barriers to entry is designing appropriately for vibration and the acoustics, getting the design right and economical, and just getting stakeholders to buy into something new and different from a perception issue of these performance issues. So that's sort of an intro. I also have some engineering-ish slides here to start out, but just the premise here, right, is really physics-based. It's building science around acoustics, where you have to look at that floor is your specimen, and it's a barrier for either an airborne or impact sound from the unit above, let's say, down into the floor below. So you have a source room and a receiving room, and when you test acoustically, you design your assemblies for that. And then the middle picture is kind of the way engineers look at people. We're kind of a sorry lot. So this is a diagram showing you the resonant frequency of different parts of your body, from your eyeball socket to your head. Anyways, drawing into that, this acceptance criteria perception on vibration really comes around the resonance of a floor with your abdominal mass, which resonates between 4 to 8 hertz. So you can use that at dinner party conversation this weekend. Really impressive. But it's good to just kind of dial back. And these are kind of not life safety issues. These are, it's hard to define the acceptance criteria. What was acceptable to me might not be acceptable to you. So once you get all the science behind it, you're still left with some uncertainty on what the right acceptance criteria is. And you have to wrestle with that. So then without those things, you really get to assemblies. So this is just a representative CLT floor assembly where you get buildups. The CLT floor itself is not going to do it. This has a hung ceiling. It has a lot of topping on the top. There's specific flanking strips around the sides to make sure the sound doesn't transmit. So quite a bit of thinking goes into the detailing of a full building assembly. So quickly on the motivation, this is a residential floor assembly piece. So at Katerra, where we're going to be working with development partners and do a whole bunch of floor assemblies, we want to get this design right. And once we crack the nut on a representative apartment unit, we can repeat it hundreds or thousands of times based on some preliminary testing that we've done. So that's the motivation. We're also looked at topside assembly options. Architectural exposed ceilings is an advantage, but also letting the wood do as much as it can for you. So the fire resistive rating is going to come from charring of the wood, not a sheetrock on the bottom. I won't go through all of these, but we did want to benchmark performance against a light wood frame joist floor. We needed to benchmark against something because, again, the acceptance criteria, it's really good to benchmark. So we chose joist floors. A lot of our development partners are working in that space, and I've really never seen performance data the way you'll see it's measured, and from Arup here in a moment, on that as a baseline. And then full-scale testing. So now I'm on the product side of the world and not a consultant anymore, so we have the time, resources, and motivation to actually go test it and get the evidence, which you need for at least acoustics on the piece of the equation. So, and IBC was key. Europe, you might look at assemblies from other countries, and you really learn after a while that their criteria are often much more stringent than ours. So if we're working with our clients here in our code, the baseline at least has to be the minimum of the IBC, and that can fundamentally change your assembly that you're going to come up with. And then we're focused on the vibration acoustics, but the other design criteria are structural and fire. And that's a little show off of kind of the different user experience that we want to pull off with this could be a market rate type 5 construction, and if you can expose that wood ceiling, it's a differentiator. Quick thing on design methods, just there's kind of crude methods out there, especially in wood choice, rules of thumb. I remember, I don't know where I learned this, but it's easy to just design for a tighter deflection criteria. And there's some recommendations to do that, but it's not really science-based, I'll say. To Weyerhaeuser's credit, though, recently they've created the TGI Pro rating system. It's kind of a proprietary algorithm, so you can't really get into the, it's a bit private, but it's based on testing, and they give you a dial here. You can work with your client to have kind of really low performance up to really high performance, and we use this to size our joist floor for the 84% target, which would be a value of a pro rating of 45. And that created a benchmark. In the world of CLT, we approach this as a design problem with looking at different methods. There's Gratz has a CLT designer that actually captures 3 of these 4 methods. We did the FPA innovations method, and they all give you different answers. I'm going to move quick so I give time for my friends. We had a representative apartment unit, so we targeted a 16'6" span with a 12-foot backspan, kind of maximizing the bigger units we designed to. That would control the design. What did I just do? I don't know what that was. Then, yeah, one more slide. And this is a summary. We took a lot of manufacturers and their catalogs in the book. This is way back in 2016, well before we started the testing program. And we took those spans and we looked and said, okay, what are the controlling limit states? It's never strength. It's never fire, in this case, a 1-hour fire rating. It's never deflection. It's vibration. And you can't really see the colors too well there, but we had them either green or yellow. And the footnote says we kind of worked out until we got to a span. But green would mean you're okay in all 4 of those vibration checks. Yellow meant you passed some, but not others. So without more test and data, as an engineer, you're probably going to the conservative end of the spectrum because you don't have enough information to do anything else. And our motivation was to get out there and prove we can go further. And we did test this 160 millimeter and 140 millimeter CLT assemblies. So we had 2 thicknesses in our test program. Is that a good point to hand off to Denis, I think?
Thanks, Hans. Yeah, so my name is Denis Blount. I lead the Acoustics AV and Theater team for Arup in Seattle. And we were super geeked to work on this project with Katerra because it's one of the goals was to really push the boundaries for how lean and mean we can make this CLT assembly that still meets IBC requirements. So, one of our first big ideas was, if you look at a lot of the pre-tested CLT assemblies out there that meet the IBC requirements, a lot of them are what I would call a single panel acoustic concept, right, where you pile mass and sometimes resilience on top of the CLT to meet the minimum performance requirements. And we know from a first principle standpoint that a double leaf acoustic assembly that uses a mass, an airspace, and another mass can provide you with more performance with less weight. So right off the bat, that was like a really attractive concept to start from. So from there, it was really, we knew what the CLT base was. It was, let's design this airspace and mass acoustic topper that goes on top of the CLT. As Hans mentioned, though, there were a couple CLT options in play. So we started by going through a bit of a sensitivity analysis to look at the range of CLT products that were being considered and trying to understand what sort of delta and acoustic performance we could expect from all of these slightly different CLT slabs. And luckily, we found pretty quickly that there's only 1 or 2 either STC or IIC points difference between all of the various CLT slabs under consideration. So that gave us a lot of confidence to move forward with this acoustic topping design that could be somewhat independent of the final CLT selection. And from there, we did a relatively quick but wide net of a literature review. Again, this was back in 2016, so there wasn't a whole lot of acoustic test data. So we also leveraged the global Arup network. You know, there had been a lot of projects down in the UK and Australia that we could look to. And also some of the building regulations in other countries just have a lot of assemblies that aren't commonly used in the US, but that was no reason not to look to them for inspiration. And in the end, we couldn't really find an assembly that sort of ticked all the boxes that Katerra was after. So we took more of a sort of hybrid design approach that combined the empirical data that we had available. We used some commercially available acoustic prediction software to come and sort of test some prototypes virtually. And then just first principles too was a big part of our initial analysis and brainstorming around what we could possibly do. So out of that came 6 possible prototypes, which I've summarized here. I won't go through all of the options, but the idea was to take these 6 concepts and work with Katerra's construction arm to do a bit of a stress test on them and see how each one stacked up with respect to weight and cost, constructability, logistics, et cetera, right? This is becoming a product. It's going to be rolled out a bunch, so we couldn't look at it from just our little acoustics vacuum. We'll skip over, or we'll skip ahead to the one that was sort of the preferred design option or the most attractive design option. This assembly was inspired by a UK floor system that uses 1 to 2 inches of mineral wool to float a finished floor over top of a concrete slab. And to our knowledge at the time, this hadn't really been tested in the mass timber world, but it looked like a good precedent for multifamily housing. And again, from a first principle standpoint, there's no reason it couldn't work with mass timber. And the real, I guess, intrigue, or what we thought was especially attractive about this, is that this floating mineral wool layer does sort of 2 acoustic things at once. One, because it's this porous material, it kind of acts as a quasi-airspace, so we were able to pseudo-achieve that double leaf design that we were looking for. And 2, mineral wool has a bit of give to it, right? So it adds resilience to the assembly, which can really improve your impact sound isolation, which is often one of the more challenging things to solve in mass timber and otherwise. So this was vetted pretty heavily with the Katerra construction folks, and I think it was also quite attractive from a cost and constructability perspective because it uses, it's pretty simple to construct. It doesn't rely on these like resilient channels or resilient underlayments. It's made of pretty common and economical materials, and the sheet good layer that sits on top of the mineral wool, you know, there's nothing magic about the MDF or the plywood, right? So actually, we could use any variety of sheet good materials, and as long as we achieve the same surface mass or the weight, we could sort of vary. We've got some flexibility in how the whole thing comes together, which was attractive as we're talking about building around the country. From there, we just needed to make sure it worked. You may have noticed that the predicted performance of this prototype option was right at the edge of the IBC requirements. So we were a little nervous about it. But we felt like overall it had legs, and the fact that we were going to full-scale build this thing and test it, we felt like we could make adjustments in the field if needed to improve performance. There was actually a lot of design thinking that went into the stacked prototype thing that was built in Katerra's factory in Spokane. But I think we'll just sort of skip over all of that and get right down to how it actually performed. For Peter.
Thanks, Dennis. I'm Peter Dodds with our Acoustics AV and Theater team in Seattle at Arup, and actually conducted the measurements on the prototypical floor assembly, so I'll run us through some of the results and see how we did. So, as we mentioned earlier, the IBC criteria was really what we were going after. So we were trying to meet a field-installed performance of AIIC 45 and FSTC 45. So both impact sound isolation as well as airborne sound isolation. And we really wanted to make sure that we could benchmark those against a common industry standard. So we also performed all of the tests we performed on our CLT prototypical assembly against a standard TJI floor. Additionally, we also did, slipping back. Additionally, we also looked at some low frequency performance that's not captured by the ASTM standards for impact and airborne sound isolation, but has a pretty heavy perceptual weight for how we experience sound isolation. We also looked at vibration from footfall and impulsive sources. So to dive right into the acoustic results, the graph that's on the screen right now indicates the airborne sound isolation performance for the various floor assemblies under test. Just to orient you, the horizontal axis is a frequency in third octaves, and the vertical axis is the field transmission loss of that floor assembly with respect to airborne sound. So the higher up on the line the graph is, the more sound it's attenuating at a given frequency. So our target to hit via the IBC is FSTC 45, which is in essence just a single number distillation of the sound isolation across various frequencies. And I've indicated it there with the green is above FSTC 45. So the dashed lines you're seeing below are just the CLT panels alone, no topping slab or additional finishing. So bad news if anyone's trying to do exposed wood floors and exposed wood ceilings. It's not going to work. They fall quite a bit below the FSTC 45 target, so they're FSTC 37 and 36 respectively. But we can see once we add that additional topping slab built up of the fiberglass and the MDF and the plywood, we get a pretty dramatic increase in our airborne sound isolation performance up to FSTC 51 for our 140 millimeter CLT slab and 52 for our 162 millimeter FSTC slab. So the increased mass of those topping assemblies as well as the performance of the absorptive airspace seems to be giving us quite a bit of additional sound isolation that we weren't getting ahead of time. So this is good news for us. It shows that our CLT assembly is meeting the IBC requirements, and it also shows that it's without incorporating any sort of finished flooring or floor assembly. So it gives us a lot of architectural flexibility. Looking now at the impact sound isolation performance of our assemblies, due to the lightweight nature of CLT, this is traditionally an area where we've struggled to meet acoustic performance criteria. And just to orient us again, there's on the horizontal axis the frequencies were involved, but this time we have normalized sound pressure level on the vertical axis. So if we just reverse our brains, a lower line on this graph is a higher level of sound attenuation. So the important target to hit here is a IIC 45, similar to STC, is a single number distillation of the performance across various different frequencies. And we can see with our dashed lines again, just the CLT by itself without any topping slab, we are not getting into the range at which we have acceptable performance. But when we add in our topping slab without a finished floor, that's the blue line there, you can see that we're reaching AIC 47. So without a finished floor, just with the acoustic topping mass, we're already meeting the IBC criteria that we've set out to do. We also tested 2 finished floors, just a 20 millimeter click lock vinyl flooring with a pad on it. And that's our green line. You can see we get a similar AIC performance, but with some increased attenuation at high frequencies. But because we're being driven by the low frequency performance in that little red circle, there's only a change of AIC of 1 point up to 48. So this is also a good indication of a time when a single number acoustic metric isn't really giving you the full story on how this partition is performing. Finally, we tested with carpet, and you can see a dramatic improvement there in sound attenuation down to AIC 62. So pretty dramatic improvement with the addition of the carpet, but all of our floor assemblies that we tested with the CLT 140 mil ended up meeting the criteria we were aiming for. You'll see a similar story here with the 162 millimeter CLT. So again, nothing on the CLT, we won't meet our performance, but with the addition of that acoustic topping slab that we laid out before, we're already meeting the IBC standard of AIC 45, achieving AIC 50, as well with increased high frequency attenuation with the addition of the vinyl tile, or if we replace it with carpet, getting a significantly higher amount of sound attenuation for impact noise. To compare this to the industry standard, or just like a industry standard TJI, you can see without a finished floor, so just the TJI with no additional mass on top of it, we're well above the AIC criteria of 45, achieving only 34. But what's different here compared to our CLT is that when we apply a luxury vinyl tile or some other hard finish flooring, we're not seeing the same dramatic increase in performance because we're not getting that additional mass or that additional resilience that the CLT panel gives us. And so we're still not achieving the required performance target. We're only achieving AIC 35. The only way that we found to get our TJI assembly to meet the IBC criteria was by applying carpet. So it provides us a lot less flexibility from an architectural design standpoint to what we can actually do. So just looking at the CLT, this is without finished floors. Against the TJI, you can see our TJI line is quite a bit above, while both of our CLT assemblies are meeting our IBC requirement. With the addition of the luxury vinyl tile flooring finish, our TJI assembly is still above the required IBC target, but both of our CLT finished floors are now meeting the requirement. And it's really just with the addition of carpet that the TJI is able to meet the AIC criteria. We also looked at some low frequency performance, which is outside the prescribed standard, but has a heavy impact on our experience of sound isolation perceptually. So you can see the various airborne sound performance for the various different types of partitions we looked at. We also looked at a 6-inch concrete slab, a bunch of laboratory tests from a 6-inch concrete slab, which is that line. And to orient us, again, high lines are more sound attenuation. So we can see that the CLT and TJI floors are performing below a traditional concrete slab, but we can also see is that our CLT floors are performing significantly better than the TJI floor by about 10 decibels at some low frequencies, which is significant. Looking at the impact isolation, so switching our mind to think that the lower lines are better, we can see that concrete is still providing us with the lowest level of sound transmission, but that our CLT is still about 5 to 10 decibels better than the TJI above 80 hertz. Lower than that, and the difference between the CLT and the TJI becomes a little less significant, but it's still perceptually relevant to how we might experience sound isolation in situ. We covered vibration quite a bit in the first presentation, so I'll sort of slide through these a little quicker. But as was noted, when people walk on floors, they apply dynamic forces that cause those floors to vibrate, and that vibration is usually small and not perceptually visible or significant, but it can often be felt. So we felt like it was an important thing to test. So we looked at measured footfall response, typically given in response factor, and saw how our floors stacked up. So the plot at the right shows the footfall results for each of the floor assemblies at various different walking frequencies. The TJI floor is in orange, the CLT 140 millimeters is in blue, and then the 162 millimeter CLT is in fuchsia. And we can make the following observations. The 140 mil CLT assembly generally gives similar performance to that traditional TJI floor. The 140 millimeter CLT gives slightly higher response factors actually for lower walking frequencies, but not significantly so. What is significant though is the performance of the 162 millimeter CLT panel, which is a step change actually in the improvement in the response factor compared to the industry standard TJI. So our vibration measurements are echoing what our acoustic measurements have indicated to us, and that the CLT assembly presents a viable alternative to TJI floor assemblies with respect to the acoustic and vibration performance, and even exceeds the performance of the TJI for various metrics we looked at. Additionally, CLT allows us the flexibility to utilize various flooring materials while still meeting our code requirements, and can have all of the advantages inherent in CLT construction. So I think that's it. We'll have time for questions later, but otherwise, thank you very much.